All right, so last time we finished on this idea of compounded interest. And there's two formulas. And they fall into sort of a category of discrete and continuous. Continuous you can think of as all the time, constantly running. Discrete says, let's break it up. We're going to break it up into a finite number of pieces. And now the question is, okay, well, how do you figure out what your interest is? And in particular, what's your current investment? I like to think of this in terms of investment. So we have some pieces. Let's sort of quickly remind ourselves. There's an initial amount, and that's the same in both cases. Now let's focus on discrete. You have a rate, R. Now normally, rates are given as percentages. So rate as a percentage might be something like, let's say 6%. But when we talk about this R, in the formula, don't put in 6. What should you put in? What do you do with percentages? Yeah, you have to convert it. So 6% says our R is 0.06. Essentially, it's like 6 over 100. As someone said, divide by 100. So make sure you're putting in the right number. Otherwise, you might think, my goodness, making money is easy. I'm getting huge returns. Now, M is the number of times per year. Now, what's going on here? Well, the idea is, say, let's do it once every month. So each month. Now, the idea is you're getting to have 12 times over the course of the year, you're getting some return. And it gets folded back into your investment. And so this is useful because you get to get interest on top of interest. This is where growth really starts kicking in. So if we do each month, that corresponds to M equals 12. So what should happen? Well, normally you say it's 1 plus a little bit. So the 1 plus is you have your initial amount still there, plus a little bit extra. So this is you keep your current amount, plus you add on a little bit. Now, what do we want to do? Well, if we're doing 6% per year, we don't get 6% each month. How much do we get each month? Well, you take 6% over 12. Because you're chopping it up and saying, look, that's really 0.5% each month. And over the course of the year, if you add 0.5 up 12 times, you get up to 6. Which really, again, you have to say, well, that really, when we convert it, that says our R over 12 would be 0.005. So it's a small number. But that's okay. The key is we're going to multiply by 1 plus a small number many times. And that becomes big. All right. So that's our discrete one. But we also have our continuous one. And it just turns out, beautiful fact, that if you let M get bigger and bigger, it approaches this special number, E raised to the power R. So E is a very particular number, very famous, 2.71828. All right, so these are our formulas, and they're going to play a role, not just in today, but in our next chapter. So we're finishing up a chapter today. Next week we start a new chapter. So let's see if we can do some examples here relating to these formulas. All right. A person, oh, that's good, person wants to have $15,000 cash for buying a car 5 years from now. Now, I will say almost all these examples come from the book, And I changed one word. They said, oh, they want $15,000 cash for buying a new car in 5 years. And I was like, no, this book is out of date. $15,000 will not buy you a new car. But okay, so I just said a car. All right, so how much should be placed in an account now, paying 6.7% compounded weekly? Compute the answer to the nearest dollar. Well, what's going on? We know it's about compounded money because there's this compounded here. And weekly says we're in our discrete setting. And what are we after? Well, it's how much do we want now? So if we're talking about how much we want now, what is it we're asking about? What could we be after? The initial, yeah. The initial amount. So we're after our initial investment. So, because we know how much we want then. Then we want $15,000. The question is, how much do we need to put in now? So we say, well, look, we want $15,000 then. So that's $15,000 in the future equals our initial investment, C. That's what we're trying to solve for. And now we just go through and we put all these pieces together. All right, 1 is 1. R, well, this is given to us as a percentage. And so we do our quick move the decimal place over 2. So it'll be 0.0675. 0.0675. M, number of times per year. What goes there? How many weeks in a year? 52. So M is 52. 52. And number of years? Well, we see the word years here. It's 5. So the good news is, this is a number. It's some quantity. It's just a matter of finding it. And so now, let's see if we can't find that. I have a calculator here. Don't know how well this will work. I'm an old person, so bear with me as I try the technology. So I'm going to focus on finding this number. So I'm going to take 1 plus 0.0675 divide by 12, and I've put that in parentheses, raised to, parentheses, 52 times 5, parentheses, equals. Okay. Now, what do we get? We get the number 4.29908 ... Sorry, what? Why should I divide by 12 instead of 52?
On the calculator, you divide by 12.
Oh, did I divide? Ah, my gosh. Oh, you're right. I'm sorry. All right. Take away my calculator badge. Got to go let the Boy Scouts know. Okay, clear. Okay. Try that again. Parentheses, thank you. 1 plus 0.0675. Divide by 52, parenthesis. Caret, that just means raised to the power, parenthesis, 52 times 5. Okay, there we go. Okay, good. 1.4011. All right. ... Now, how do we get C? Move it over. So C is this 15,000 divide by 1.4011. And let's see, are we lucky enough? I think if you hit this x inverse, that'll take 1 over. So that's the 1 over the inverse. And then times that by 15,000. And we get $10,705.62. Well, we can't put it in a fraction of a penny, So that's how much we should put in now. So if we put in 10,000, whoops, I can't even read. $10,705.62. All right, there we go. That's how much we should put in now. All right, so there you go. Double check your work. So that's the idea. And you should ask yourself, is this a reasonable answer? You might say, how do we know if it's reasonable or not? Well, just sort of like do a back of the envelope computation. In the course of a year, if you put in a little over 10,000 at roughly almost 7%, how much money should we get? About $700 a year. Ballpark. How many years are we doing this? 5. All right, 700 times 5 is roughly 3,500. At least we're in sort of like the neighborhood of 15,000. We're a little short, but that's okay. We're not taking into account interest building on interest. So it doesn't hurt to ask, does this sound reasonable? For instance, if our answer had been $10, would that be a reasonable answer? If I invest $10 today, in 5 years I'll have $15,000. I mean, that would be nice. Doesn't work. But all right, at the danger of making multiple mistakes, we'll try this again. Find the value of an investment of $24,000 in 7 years if it earns an annual rate of 4.35% compounded continuously. All right, so this 24,000 is something slightly different than last time. See, in the last time we wanted to say in the future we want $15,000. This says we have $24,000 now. So in terms of our formula, we have this C e to the RT, and we'll just throw a number here, M, a symbol here. So now the 24,000, that's our C. Our R, 4.35% becomes 0.0435, and our T becomes 7. So what do? We punch all of that in. All right, so let's try this again. So we're going to take 24,000 and times that by, and then you should have a calculator that has an E to the button. And come out. Ah, it's up here. See, there's this ln. They often go together. We'll talk about why that's true. So it's E to the 0.0435 times 7, and it tells us what? We get out a number. 32,542.72. Again, we're talking about money. Can't have fractions of pennies. Okay, so that's very simple examples of things we talked about last time. All right. Well, on to today. A quick thought for today. And we don't actually know who said the following. A lot of people get the credit for it. But it goes, I am a great believer in luck. And I find the harder I work, the luckier I get. And there's a lot of truth to this. I can look back at my own life and say, well, I've been very lucky. I met key people and I had key situations happen, and that got me to where I am. And I feel like I'm, an upright citizen, living a decent life. And but I also know that these weren't just random things. They were opportunities. And you have to learn to get the opportunities, and then you have to be open and take them. You can't just sit and wait for good things to happen. You have to work. Put in the work, and unfortunately, sometimes you have to be patient. But as long as you keep working, the opportunities will come. Don't let them pass by. Take advantage. Take advantage. Now, we're talking about logarithmic functions today. Last time we talked about exponential functions. So exponential functions were where we had the x, our variable, upstairs. And now we're going to talk about logarithmic functions. And essentially, we're going to talk about the idea of inverse functions. So you should think of the inverse function is undoing the log. The inverse function of exponential is log, which means that log is undoing exponential. And so, since it's tied to exponential functions, we're going to get some really nice properties of logarithmic functions. And if this was your grandparents taking a math class, they would actually spend a lot of time talking about logarithmic functions. You can go and ask them about something called the slide rule. They can tell you stories about this. Or maybe they'll say, oh, you should ask your great-grandparents about that. But the logarithms played a very pivotal role in the history of computation. And so they're important for us to know. So we're going to talk about them. So let's quickly talk about inverse functions. We've talked about functions before. You have an input, you plug it in, the function does something, out comes the output. Great. Now the question, can we run it backwards? So in other words, hey, I got the output, let me throw it back into the machine, have it run the computations that it did backwards, and get the input out. Put another way, I know what the output was, can I say what the input was? Now, the answer is maybe. Maybe. Not every function can do this. The problem is that there are functions where you have different inputs giving you the same output. And these are not very exotic functions. We're talking about functions like x squared. Wow. Right? Because what happens? You plug in 1. 1 squared. 1. You plug in -1. -1 squared. 1. And so we had different inputs giving us the same output. So we say, okay, what do we need to be true? And we say, well, each output is associated with a unique input. And there's a fancier way to say this. We say the function is 1-to-1. For every input, I can pair it up uniquely with a single output and vice versa. Now, we can do this graphically. We talked previously about, hey, a function has something called the vertical line test. You draw the graph, draw a vertical line. Now, when we draw a vertical line, we're saying, let's just look at the input associated with this value. And we want only one output, so we can only hit the curve at most once. A horizontal line says, now, let's look at the outputs. We want to make sure that for any horizontal line, we only want to hit the curve at most once. If we hit the curve multiple times, that means that we have that output that corresponds to the height of that flat horizontal line multiple times. So really quickly, we have some graphs here. And there's a question. Which of the following is the graph of a function which has an inverse? Is this the graph of a function which has an inverse? Horizontal line test. Can we draw a horizontal line that hits it multiple times? Yes. So this does not have an inverse. This, by the way, cheat sheet, this was the trying to look like x squared. So y equals x squared doesn't have an inverse if you just say y equals x squared. But you might notice the one to the right looks suspiciously similar. Does this have an inverse? Yes. it has an inverse because every horizontal line hits at most once. There's some that don't ever hit it at all. That's okay. But no horizontal line hits it multiple times. This is y equals x squared for x greater than or equal to 0. So oftentimes what we'll do is, if we want to talk about an inverse and the function doesn't have an inverse, we say, well, let's just sort of cut off a piece of it so that just that piece by itself has an inverse. We'll talk about that inverse in just a minute. This is looks like an exponential function of some sort. Does this have an inverse? Yes. Again, we can do the horizontal line test. So we should say this is a no, this is good, this is good. How about this? Is this the graph of a function which has an inverse? Sorry, what? Thought I heard something. Yes? No? Does it pass the horizontal line test? Yes. But wait. Does it pass the vertical line test? No. So it's not the graph of a function. So even though it passes the horizontal line test, it's not the graph of a function, which has an inverse because it's not the graph of a function. So this is a no. So this is not a function. So, all right. Well, some notation here. When f is invertible, we denote this by f inverse. And we say if y equals f of x, that says you plug in x into your function, out comes y. Well, if you run it backwards, it says, okay, now plug the output into your inverse. F inverse of y would equal x, what you had to plug in initially. Now, be careful with notation. This is a place where it's easy to make a mistake. F inverse of x is not the same as 1 over f of x. And 1 over f of x is f of x to the power minus 1. Notice where you put your minus 1 matters. Now, we don't need to worry too much about inverses, so we just want to know a couple of basic ideas. One of them says, suppose I start with a number. I run it through the inverse, and I run it back through f. What comes out? Well, what you started with. Suppose I start with a number. I run it first through f, and then I run it through f inverse. What comes out? What you start with. So you can think of it as whatever the function does, the inverse undoes, and vice versa. So they're undoing each other. Now, one thing that's true is that graphically we can sort of understand things by saying, oh, if I have a point a comma b on the function, that means you plug in a, out comes b. Then for the inverse, you swap the roles. So it's b comma a is on the inverse. What does that say? Well, it says there's this really cool fact that says, if I have a function which is invertible, so here's that square root of x, what you can do is you say, all right, there's this line, y equals x, and you imagine that you take the curve, pick it up, turn it over, and put it back down. So we're flipping it across that line. So if we flip it across that line, then, whoops, this was supposed to be x squared. Sorry about that. Then we get this curve. And this is f inverse of x, which is square root of x. Now, 2 to the x, unfortunately, I drew this a little bit off. But what happens? Well, again, you pick it up, and you turn it over and put it down, and you get a function that looks like this. So this is f inverse of x. And this is our goal of what we want to talk about. So I can get my next page. The real meat of today. Logarithmic functions. Reason we built up the idea of inverses is so we could specifically talk about this one really useful inverse. We have exponential functions. They play a big role. They model growth. A lot of things get explained by growth. And so we want to be able to work with them. And in particular, sometimes we want to be able to figure out what's happening upstairs. So we need a way to handle that. And we do that by doing the inverses. All right, so we get our logarithmic functions. So here we have y equals b to the x. So we should think of this. This is our f of x. This is b to the x. So we have our f inverse of y. It's the logarithm. Now we have to be careful because there's many choices we could have made for that b to the power x. And so we have to specify, well, which b, which is why we put a log sub b. So there's different logarithms out there. The one useful fact to know, which we don't need to worry too much about here, is that all logarithmic functions are essentially the same up to scale. But we'll put a subscript here. So we're going to talk about this function. Because we know it comes from the inverse, we'll put it again here on this page. If I start with an exponential function, so here we have our y equals b to the x, we can always find the logarithmic function graphically by flipping. So we get here our, this is y equals log base b of x. And this will help us talk about various properties. So, what can we say? Well, we talked about the exponential function. We said last time that you can plug anything into an exponential function. Its domain is all numbers. Now, when we go to the inverse, the logarithmic function, when we do our, pick it up, turn it over, what happens is we swap domain and range. So if our domain for the exponential function is all numbers, our range for logarithmic functions is all numbers. On the other hand, we said, the range of exponential functions, the only thing we can get out of an exponential function is a positive number. It's an optimistic function. So, again, since we swap domain and range, that says the only thing you can plug into a logarithmic function is a positive number. We mentioned that we have an y-intercept at 1. When we flip, what does the y-intercept become? An x-intercept. So, since b to the 0 equals 1, we always have that log of 1 is 0. We also can say log base b of b is 1. Well, why can we say that? It comes down to this type of relationship. And more generally, if I'm looking at log base b of a is equal to c, okay, there's a bunch of numbers here. That's the same as, I'm just coming here, I'm just changing y's and x's for different symbols. So I'm rewriting the same thing just with different symbols. That says what? I'm trying to figure out a is equal to b to the power c. So if I'm looking at log base b of a, my question is, what do I need to raise b to what power to get a? So b to what power gives me b? The answer is b to the first power gives you b. So that's why log base b of b is 1. Log base b of b to the n, well, if I want b to the n, I need the nth power. So that becomes n. If log base b of x equals log base b of y, that says the insides have to match. X equals y. This comes back to our idea. If b to the a equals b to the c, a equals c. Almost everything that's important about logs comes from exponentials. So, to make it more clear, b to the x, b to the y is b to the x plus y. So if you multiply, you add the exponents if the downstairs match. We can turn that now and say, well, what does that mean about logarithms? Well, it says the following. Log base b of p times q becomes log base b of p plus log base b of q. In other words, logarithms turn multiplication inside into addition outside. In a similar way, b to the x over b to the y is b to the x minus y. So notice here we're dividing, we get subtraction upstairs. Well, that becomes the log of p over q is the log of p minus log of q. So division becomes subtraction. And we have one other, b to the x to the power y is b to the xy. And that says what? Log base b of p to the power q is q log base b of p. So in other words, raising to a power comes down and becomes multiplication. Now, these properties of logs, this is why logs played a huge fact historically. Because it turns out that addition is considered pretty easy. When it comes to computation, people were happy doing addition. They just like, I get it. I understand how to add. But multiplication turns out it's a lot harder. It's more computationally intensive and took a lot of time. And so they faced challenges in that they had to do lots and lots of computations that involved multiplication, and it was becoming overwhelming. They couldn't keep up. And then the idea of logarithms came. And it was the great light bulb that said, wait a second, we can transform our complicated things into simple things. Now, what's the punchline here? Logarithms love multiplication and raising to power. A word of warning. Logarithms hate addition. They can't handle it. You have to work with what it's good at. Logarithms are good for multiplication. They're bad for addition. A few more notes to make. There's two special bases. So we talked about log base b, but there's two bases in particular that show up over and over again. If you were in computer science, we'd say there's three bases, but we're not in computer science. This is not that kind of a class. So the two bases that show up are 10, and because we work in base 10, so we work in powers of 10. Think back, we did scientific notation. So we'll call base 10 the common log. And we'll just not use a subscript here. So if you ever see log without any subscript, think of that means base 10. The other one is what we call the natural log, and we use that number e. So that 2.71828 number. And we denote this by ln. So if you see ln, that's natural log, and means log base e. The other thing to point out, Log base b of b to the x equals x. Why is this? Because we have inverse functions. This is that f of f inverse. Gets you back to where you started. Same principle, b to log base b of y equals y. There's a little bit of a caveat here. We can only do this if y is positive. Why do we need to add a caveat? Well, for which values of x do we get things that make sense in the first expression? And the answer is for all x, this will make sense, because b to the x will be positive, regardless of what your value of x is. And then you're taking log of a positive thing, so that makes sense. On the other hand, in order for us to make sense here, we have to say, well, what's log of y? Log only makes sense if you plug in a positive thing. So there's a restriction coming into play. So be careful. Make sure what you're plugging into log is positive. All right, any questions before we jump into examples? All right. The main thing, if you know this, everything that follows will be straightforward. Okay. So we'll do some quick warm-ups here. We're looking for log base 10 of 1,000,000, and we're not going to use our calculator. What's another way to think of 1,000,000? Well, since we're working in log base 10, we don't actually need to write the word base 10, so we could just say log. So I'm going to think of it as 10 to something. Because if I can write it that way, then I have a chance. And the question is, what's the something? How can you think of 1,000,000? How many times do you have to multiply 10 together to get 1,000,000? 6 times. So 1,000,000 is 10 to the power 6. Okay, so what is log base 10 of 10 to the 6? What's the rule tell us about logs? Since this matches that, you say, then it's what's left, it's what's in the exponent, so it's 6. Okay, log base 2 of 128. I mentioned computer science has a third log that they like, and that's log base 2. And turns out, 128, can we write that as 2 to a power? The answer is yes. Is anybody good with their powers of 2? Sorry, what? You never... 7, yeah. You know, it's that fun game we play as kids where we start working through our powers of 2. 2, 4, 8, 16, 32. I usually get to about 65,536 before I tap out. All right, so 7. All right. ln of e to the negative 3. Don't worry, we're still in our warm-ups. What will this be? And remember that ln is the same as saying log base e of e to the negative 3. So what do we have? We get negative 3. Log base 3 of 27? Well, 27, also known as 3 cubed, so our answer is 3. 2 to the log base 2 of negative 5 is? Does not exist. You can't do it. Why not? Because you can't take log of a negative number. All right. solve for x and or b. We come over here. Now, the first one, we're trying to figure out our base b. So, how could we do this? Well, one way is to say, if I'm asking the question log base b of 1 over 25 equals 2, I can turn it into a different question. Because a logarithm means something. So this is the same as asking the question, take the 1 over 25, and you say that's equal to that b, that base, to the power 2. So asking for which b does log base b of 1 over 25 equal 2 is the same as asking 1 over 25 equals b to the power 2. What's b? So written in this way, this looks like a question we can answer. What would we do? How would we get to the root of this problem? Well, we would take a square root. Square root of 1 over 25? 1/5. Now, at this point, you're probably saying, Steve, you forgot something. You forgot the plus minus. Or did we? So we have to be careful. You should always at least think, wait, do I need a plus minus? In this case, we don't worry about the plus minus because we're looking for something where we're taking log base b. The only thing that makes sense is b needs to be a positive number, but not 1. And why restrict ourselves to that case? Because those are the assumptions that we made about exponential functions. So we still have those assumptions coming into play. So we'll just make a little note. Note, b has to be greater than 0 and b cannot be 1. So that's why we don't need to worry about the negative 1/5. All right, we'll play a similar game here. Log base b of 10,000 equals 2. What is b? Convert it. What is this asking us? $10,000 equals b squared. Can we take the square root of 10,000? Yes. And we get 100. All right, log base 4 of x is 3/2. Okay, so now it's the x we're trying to solve for. So in essence, we're trying to get the x out of the log. So x is inside the log function. So we can do two things. They're both essentially the same. One is we can say, oh, this is a matter of rewriting. And the other way is to say, oh, if I want to get something out of the inside of a function, I use the inverse of the function. So if I raise both sides, so I take 4 to the left-hand side equals 4 to the right-hand side, 4 to the log 4 of x, this is a function, an inverse function, together gives us x. They undo each other. Then we get our 4 to the power of 3/2. This is the same thing we've been doing up here, just in a sort of a slightly different mindset. 4 to the 3/2, you can think of this as 4 to the 1/2 cubed. And I like to think of it as you're doing two things. You're making something smaller, that's the 1/2. You're making something bigger, that's the cube. 4 to the 1/2, 2. 2 cubed, 8. 2, 4, 6, 8. Who do we appreciate? Logs. Logs. Yeah. Okay. All right. Well, we'll work on that song. All right. Solve for x. We have 2 of these. I think we can probably finish one, maybe even both. Which one do you want to go through first?
First one.
First one. All right. Bold strategy. Do it in order. Okay, so I'm going to think of this by saying, let's merge these together. So I'm first going to say, hey, I can bring what's in front of a log inside. But if I bring it in, how does it come in? And the answer is it comes in as in power. So this is equivalent to log base b of 4 to the 3/2 minus log base b 8 to the 2/3 plus log base b 2 squared. Now, 4 to the 3/2 we just talked about. You take it to the 1/2, and then you cube it. That's 8. 8 to the 2/3. Take the cubed root, then square it. You get 4. Log base b of 2 squared is log base b of 4. Do you notice what we can do? Cancel. We have log base b of x equals log base b of 8. Well, if we have log of something equals log of something means the insides have to match. So our conclusion is x equals 8. Now, I have a few seconds. Log plus log becomes multiplication. Addition becomes multiplication inside. Log equals log says, hey, drop the log. This becomes x squared minus 4x equals 21, or x squared minus 4x minus 21 equals 0. That factors as x minus 7 times x plus 3 equals 0, which says x equals 7, or x equals negative 3. So, how many solutions do we have? And why is the answer not 2? Do we have 2 solutions here? We do not. We have been deceived. It is the great deceiver. You probably are thinking, wait, I can count 1, 2. One of these is not a solution. Which one of these is not a solution and why? Negative 3 won't work because you can't take log of a negative. So be careful. All right, that's it for today.